Okay, Mr. Kwong here. I'll go through question 5 and question 6. Alright, so start off with question 5. We have Newton's second law of motion. This is straight from the notes. Just make sure that you talk about, you need to have the 2 points. You need to talk about the rate of change of momentum is directly proportional to the net force and also in the same direction of the net force. Okay, so these 2 points must be there for that 1 mark. Okay, next you move on to part B. You have a car of mass 850 kg towing a trailer in a straight line along the horizontal road as shown. Okay, at time t equals 10 seconds, they give you some information that some of them are distractors, just have to be careful. 30 meters per second at 10 seconds and acceleration is 0.40 meters per second square. Right, so they tell you there's this horizontal tow bar here that connects the 2 items. Right, so you're supposed to calculate the resultant force acting on the car. Right, so let's just draw in the acceleration vector here. So this acceleration over here is just 0.40 meters per second square. Right, so the calculated net force is just F net is just equals to mass of car multiplied by acceleration. So this will be 850 kg, 850 times 0.40. And the answer you get is, wait a minute, let me scroll up. It's 340 newtons, alright? 340 newtons, alright? So that's it. Okay, some of you over complicated this. You go and find out your acceleration using velocity. There's no real need to do so, right? Okay, next you're asked to, given there's resistive force acting on the car, okay, sketch a free body diagram of the car and clearly label all the forces acting on it. Right, so you need to, when you see this clearly label, right, in fact for all free body diagrams, right, unless it's your own personal working, right, you should label them in full, right? Don't just write as F or weight or just W. Okay, so let's just quickly draw in. Okay, try to make sure that your lines are as straight as possible. Right, so let's just draw this. Okay, and then label this as weight. Okay, then we know that your weight is cancelled off by the normal reaction force, so this one should be the same length. So just going to draw it slightly to the side. Okay, oops, sorry. Back a bit. Okay, so let's go up this way, and yep. So this is, let's call this zoom in a bit for me to right. So this is normal contact force. All right. Then there's resistive force. So some of you wrote it as drag force, and some of you wrote it as friction, but that's fine. We know that the car is moving to the right hand side. Maybe we just draw in the velocity vector first, so we know that's happening this way. Okay, so let's just draw in the resistive force. Let's just label it here, resistive force. Okay, so let's call this resistive force. Okay, then we have engine force because the engine is driving the car forward. Okay, engine force. Let's draw it longer. Okay, so engine force. Okay, or we may call it driving force. That's fine too. Okay, and last we have tension. Tension is at the back this way. Okay, tension from tow bar. Right? Yep. So these are the forces acting on it. Alright, so this is your free body diagram. Let me adjust my microphone a bit. Right. Okay, going up. Okay, so given that the resistive force acting on the car is 510 newtons and the tension is 440 newtons, calculate the horizontal force exerted on the car by its engine. Okay, you can refer to the free body diagram, but I'm just going to draw a quick one here again. So let's just sketch this out. We're going to have driving force, let's call it D, FD, and then we have also resistive force, let's call it R, and then we have tension this way. Alright, and we know that the net force, we worked it out on the previous page, right? You will have a certain net force. So this F net is equals to FD minus R minus T. Alright, and F net from the previous page was 340. So this is 340. FD is what we want to find. So let's write as FD still minus resistive force of 510 minus tension of 440. Okay, so my FD is equals to 340 plus 510 plus 440, and that will give me a total of 1290 newtons, right? 1290 newtons. right? Yep, so that's it for this one over here, all right? So a lot of you again overthought it and you didn't know which one to add, which one to subtract. So it's important for you to be able to draw the free body diagram here. If you can't draw this free body diagram, it makes it very hard. And we didn't have ECF from this part here to this part here. So if this is wrong, and you follow this one will be wrong as well, all right? Okay, next, we're moving on to question 6. Question 6, you have an Atwood machine consisting of two masses connected via inextensible cord. Right, so cord is inextensible. This tells you that your acceleration of A will be always equals to acceleration of B. Okay, just that, okay, the direction will be different, of course. Alright. Right, so these are the vector quantities. Right, then they're suspended a pulley which in turn is connected to the ceiling as shown. Okay, so there's no friction here. So this is a frictionless pulley, and then it turns freely. Alright, so an Atwood machine essentially is a pulley system of two masses. Okay, both masses are 4 meters away from the ground. Alright, and are you given the masses? You are given mass A is 2 kg, mass B is 5 kg. Okay, so their ball is ball A and ball B. Okay, define linear momentum. Again, don't overthink it. It's just basically for an object is the product of its mass and its velocity. Right, that's it. Okay, so again, refer to your notes for the exact definition. You can just literally memorize this exact definition and just write it there. Alright. Next, you're asked to draw and label the forces acting on balls A and B. Okay, there's only 2 forces per ball, so there's tension and weight. Okay, but because of the fact that there's only 4 forces to draw, right? It's quite simple to draw, right? You're expected to draw them accurately. Alright, so that means you need to take into account the direction as well. The direction and of course the magnitude. Okay, I'm just going to show you some answers that I rejected. Okay, if you draw this, you're supposed to draw your tension, your forces are supposed to be vertical, so they need to be drawn clearly vertical. Alright, I have accepted some that were a little bit off like this. Okay, I accepted some that was like this. Okay, but there were some cases where the student literally drew it like this and then the ones like this as well. Right, so this is way too off. Slightly off is okay lah. Okay, is impossible for you to, if you put in some care, right, it's impossible for you to draw it slanted. Can I please use a ruler when you're drawing it? Alright, so again, let's just label this is my tension. Okay, tension due to cable, and because it's the same cable, right, I expect B to have the same tension as well, so I'm going to draw in roughly the same length. It has to look okay, if you can't be fully bothered to draw the same length, right, at least it must look believable that they're same length. Okay, you cannot look clearly of different length. That's the most important thing. Alright, okay, and we look at this system, right, even without any calculation, you can tell that this system here, right, your ball A will go up, your ball B will go down. Okay, purely because of the masses. So that would mean that I expect my net force for A to be upwards. That means my weight of A should not be too big. Okay. Okay, weight of A should not be too big. Okay, and my B, okay, my B's weight, right, should be larger than the weight of A and also larger than tension. Right, so this one I can just go much longer. Alright. Okay, that's it. Alright, so that's what you have. Okay, then next you are asked to calculate acceleration of ball A, stating clearly its direction as well. Okay, if you do everything wrongly in front and you just guess the direction, right, you get it wrong. Okay, you will not get marked for direction. Alright, so let's do this. Okay, if you look at A, I always like to use the approach of deciding where the acceleration is first. So I'm just going to draw another A at the side. So I'm just draw A here. Okay, and we know that A will accelerate upwards like this. Okay, this is acceleration. Alright, so we start to form the equation. We have net force on A. So F net, okay, so this is for A. F net is equals to tension minus weight of A. Okay, so this is equals to mass of A times acceleration equals to T minus 2G. Okay, and then we can write tension as we can make T the subject. So T is equals to, this is 2A, right? So this will be 2A plus 2G. Alright, so this is equation 1. Okay, for B, let's do the same thing. For B, again, is here. This is just the acceleration. Acceleration is this direction. Alright, so weight of B will be larger. So for B, okay, it will become F net is equals to WB minus T. So this will become MBA minus MBA equals to 5G minus T. Okay, again making T the subject, so T is equals to 5G minus 5A. Alright, equation 1 and 2. So combine 1 and 2 together. I have 2A plus 2G. 2A plus 2G equals to 5G minus 5A. Okay, rearranging to find A. So we just shift things around. So we have this will become 7A equals to 3G. So A will become 7 divided by 3G. What do you get? You get 4.20, right? Let me double check. I have a calculator nearby. Hold on. 9.81 times 3 divided by 7. Yeah, 4.20. Okay, so this is 4.20 meters per second square. Okay, and this is an upward direction. Okay, so this is up, and then this is 4.20 meters per second square. Right? So this is part 2. Okay, some of you straight away jump into this line without any proof. Okay, there is loss of marks, right? Okay, if you just jump straight at this line. Alright, next up we have show that time taken for either the ball to reach the ground is 1.40 seconds. Okay, so for this one you can just use your kinematics equation. So we can do S equals to UT plus half AT square, and S is 4.0, initial velocity is 0 plus half 4.2 T square. So for T you get 1.379 seconds. Of course I rejected the T was 0 lah. And this is equals to 1.40 seconds. Okay, next, calculate by stating clearly the relationship between impulse and due to a force and linear momentum. So you have to be careful because you have to clearly state. That means you need to write a statement, alright, between impulse due to a force and linear momentum. That means you have to write something like, for example, okay, you have to say impulse is equal to the change in momentum. Okay, so impulse on the object, make it clearer a bit, is equal to the change in momentum of the object. Okay, yep. So you need to have this line here. Alright, so once you have that, you can use your impulse. Okay, so you're supposed to find change in momentum, right? You're not supposed to use the kinematics equation, so but I think because this question was not very well done, so I decided to give chance, right? But what you need to do here is that you need to find change in linear momentum, right? Okay, so what I can do is this: you have impulse is equals to F times delta T. Alright, then, and this is equals to delta P, change in momentum. Okay, to find this F, this is just equals to mass of B multiplied by acceleration times delta T times, this is PF minus P0. Okay, so this will be 5.0 times 1.40, times 4.20. 4.20 times 1.40 equals to PF. Okay, and the initial momentum is just 0. Oh, so wait. So this is just minus 0, right? And once you have this, you can go and solve for PF. Okay, so basically PF, let me just double check my calculation. 5 times 4.2 times 1.4. Okay, so I get 29.4. Okay, 29.4 kg. 29.4 kg meters per second. Okay, whether you get a 0.4 or not depends on as in whether you get 0.4 or 0.0 depends on what the substitution you use. Remember, this was about 1.339 or so. Okay, so you affect the final answer, but it should be within this range of 29 to 29.4. Okay, so that's all for question 6. Okay, and I'm done. So thank you.